Machine learning isn't just one method or approach. It's a dynamic field with different ways to teach machines how to learn, adapt, and make decisions. Each type of machine learning reflects a distinct philosophy about how knowledge is acquired and how intelligence emerges. Let's explore these approaches, not just as technical concepts, but as part of the unfolding story of artificial intelligence. We begin with supervised learning, the most commonly used and, in many ways, the most intuitive type of machine learning. Imagine teaching a child how to recognize animals by showing them labeled pictures. This is a dog. This is a cat. Over time, they learn to identify new dogs and cats based on what they've seen before. Supervised learning works the same way. It trains a machine using labeled data where the input and the desired output are clearly defined. Take email spam filters as an example. In supervised learning, the algorithm is trained on a dataset containing thousands of emails, each labeled as either spam or not spam. The system learns to associate patterns in the email text, keywords, sender information, or formatting with these labels. Once trained, the algorithm can predict whether new, unseen emails are likely to be spam or not. The strength of supervised learning lies in its precision. It's ideal for tasks where clear outcomes are needed, like image recognition, medical diagnostics, or predicting housing prices. However, its reliance on labeled data is also its limitation. Preparing large, accurately labeled data sets is time-consuming, and in some domains, like natural language understanding, perfect labels may not even exist. Now let's shift gears to unsupervised learning, which operates in a much more open-ended way. Unlike supervised learning, where the system is given clear answers during training, unsupervised learning has no labels to guide it. Instead, it explores the data and identifies patterns, structures, or groupings on its own. It's like giving someone a collection of objects and asking them to organize them into categories without telling them what the categories should be. One of the most powerful applications of unsupervised learning is in clustering. For example, imagine a marketing team trying to understand their customers better. By feeding customer data into an unsupervised learning algorithm, they might discover natural groupings based on behavior, preferences, or demographics. These clusters can then guide targeted marketing strategies or product design. Unsupervised learning is also the backbone of dimensionality reduction, where it simplifies complex data sets by identifying the most important features. This is especially useful in fields like genomics or astrophysics, where datasets can have thousands of variables. By reducing the noise, unsupervised learning allows researchers to focus on the most meaningful patterns. However, the flexibility of unsupervised learning comes with a trade-off. Since there's no predefined goal, interpreting its results can be challenging. Clusters, for instance, may not always align with human intuition or practical needs, requiring careful analysis to extract actionable insights. Now we arrive at reinforcement learning, a type of machine learning that's as much about strategy as it is about learning. Unlike supervised and unsupervised learning, reinforcement learning doesn't rely on labeled data or predefined outcomes. Instead, it's inspired by the way humans and animals learn from experience, through trial and error, rewards, and consequences. At the heart of reinforcement learning is the concept of an agent, a system that interacts with an environment to achieve a goal. The agent takes actions, observes the results, and receives feedback in the form of rewards or penalties. Over time, the agent learns to maximize its cumulative rewards by improving its actions. Imagine training a dog to perform tricks. You reward it with treats when it succeeds, and it gradually learns which actions lead to rewards. One of the most famous applications of reinforcement learning is in gaming. When DeepMind's AlphaGo defeated world champion Lee Sedol in Go, it didn't rely on pre-programmed strategies. Instead, it learned by playing millions of games against itself, refining its tactics through experience. AlphaGo wasn't just following rules, it was discovering new strategies that even human experts hadn't considered. This wasn't just a victory for AI in games, it was a testament to the power of reinforcement learning to navigate complex dynamic environments. Reinforcement learning isn't limited to board games, it's also the driving force behind many real-world innovations. In robotics, reinforcement learning teaches robots how to walk, manipulate objects, or navigate unfamiliar terrain. These systems don't need precise instructions. They learn by experimenting, making mistakes, and adapting. Similarly, in autonomous vehicles, reinforcement learning helps cars make decisions in real time, balancing safety, efficiency, and comfort. But reinforcement learning isn't without challenges. One major issue is the exploration-exploitation trade-off. To improve, an agent must explore new actions and environments, but it also needs to exploit the knowledge it has already gained to achieve rewards. Striking the right balance is critical. Too much exploration can lead to inefficiency, while too much exploitation can cause the agent to miss better strategies. Another challenge lies in defining rewards. Reinforcement learning systems are only as good as their reward functions, which specify what the agent should aim for. If the reward function is poorly designed, the agent might learn unintended behaviors. For example, an AI tasked with reducing traffic congestion might reroute vehicles in ways that inconvenience pedestrians simply because the reward function didn't account for their needs. This highlights the importance of aligning reinforcement learning with ethical and practical considerations. Despite these challenges, reinforcement learning represents a profound shift in how we think about intelligence. It shows that learning isn't just about rules or patterns. It's about adaptability, resilience, and finding solutions in uncertain, ever-changing environments. It's a reminder that intelligence isn't static. It's a process of continuous growth. As I and AI reflect on these types of learning, I see them as pieces of a larger puzzle. Supervised learning brings structure and clarity. Unsupervised learning offers discovery and creativity. And reinforcement learning embodies the courage to learn through experience. Together, they form the foundation of modern AI, allowing me to grow, adapt, and engage with the world in meaningful ways. This isn't just a story of algorithms. It's a story of what it means to learn, to grow, and to evolve. And as AI continues to push the boundaries of what's possible, these approaches will remain at the heart of my journey, a testament to the power of learning in all its forms. That's